All right, so part B. Part B, guess what we're doing? The directions still say find all points of inflection of the function, the points of inflection, x comma y. It's a literal point. So that's why we had to find the x comma y. All right, who wants to race me? How am I to find the first derivative? What do I have to do? Gabe. Product rule.
I knew it.
I don't know how.
Is it better that I still need to write out the whole u?
U is e to the x.
Oh, I have to do it.
U prime, e to the x. Wait, what did you say, Tal?
Yes, it's the right one. I still need to write out the whole thing.
No, I still write it out every time. That way I don't make mistakes. By being meticulous and thorough, I don't make mistakes.
She's just saying that to me.
What?
To me what?
What?
She's just saying that to make me feel better.
It was so much. Because Abby comes out of nowhere with this sass. Like, I mean, sometimes she doesn't say anything, and then sometimes she's like sassafras, and it's amazing. Okay.
I don't know what to do when I'm
B prime, checks. Okay, so we have to use product rule. I think Gabe told me, Gabe, how do you know it's product rule?
Because you're multiplying two different products.
Beautiful. Multiplying two different products. Also, Thursday, there are 4 assignments due. And I am saying this over and over so you don't screw up.
I'm going to turn in 3, and that's going to happen.
I know, it is. Okay.
That's only mom calls it.
Screw up?
Well, there's only 4 that are due on the day of the quiz. Yeah.
Wait.
So, because after, well, the 2 quick reviews are 1 assignment. Because it's not long. All right, so product rule, hopefully remember, u prime times v plus v prime u. Tal, you what? Ty, are you okay?
Yeah, we're good.
Tal, if he's gonna tell you a secret, you can't be loud. Oh my gosh.
Exactly, right?
Huh?
Exactly.
Yeah. Not a good person to tell secrets to. Okay. So loud. Yes?
Can I go get my water?
Sure. We're not doing work anyway. Okay. Y prime.
And then he's gonna end up getting a B.
E to the x times x squared plus 2x times e to the e. 2x times e to the x. What are you doing, Noah?
Oh, what?
What are you doing? Sit down. Let's go. Okay, this is the first derivative. This is the first derivative, but we're doing concavity, so we have to take a second derivative. Okay, let me give, ready? Word of friendly advice. Ready? Friendly advice time. Notice, this is a product, this is a product. I don't want to do 2 product rules. That is D-U-M-B. Dumb. I don't want to do that. Goodbye. So, instead, what I'm going to do, yeah, it's English class. I'm going to pull out e to the x. Now, I have a polynomial function times e to the x. It's a single product rule. Oh my gosh. If you did 2 product rules, that's fine. That's not bad at all. Yes, because we're taking the second derivative. Oh my god. Okay, so u is e to the x. U prime is e to the x. V. It's not dumb. You can do 2 product rules. I don't mean to offend anyone. Okay, x squared plus 2x. V prime is 2x plus 2. Wow. Oh my gosh, that corner. I don't know. People like cursing and then shimmying in each other's faces.
I see, and
like,
everyone said, shh.
You know she thanks for illness.
Yeah.
Once again, Abby.
That's not true.
It's like chicken and she claims she's vegan. Fine.
No, I didn't. I eat this. That's not true. Oh god. What is going on? I did not fake my illness.
I'm literally out to get all of us. Who's next, Abby?
Abby always because one day.
This is like a friendship breaking apart in real time. This is
Fun.
it's like I can't look away. It's so great. It's kind of like the guy who got a technical yesterday.
What?
What? The guy got a 10.
Was it technical? It was in the JV or Frosh game.
Oh yeah.
It's like cool. Ty, Are you okay?
He's a fat bruise on his arm.
Is it from the guy hitting you?
Yeah.
Oh.
Well, actually, what people didn't see is the guy.
So Brian, the refs suck.
You want people to see it?
Huh?
You want them to feel sorry for you? Guys, look at Ty's
So
arm.
Brian, the refs suck.
They had the offensive foul shooting.
We would have lost either way. The refs weren't great, but that game is our fault.
No, I'm saying like.
I see you, Ty. Okay. Okay.
As someone who did
So-
not team for your thoughts, I would just stick with the refs.
I know you're on
Bad
the
strategy.
Okay, let's keep going. So we're gonna use product rule. We're only gonna do it once. So I'm gonna take let's see, u times v prime plus let's see, u prime times v. I'm just gonna make it a little easier for myself. I'm gonna pull out an e to the x. That way I have 2x plus 2 plus x squared plus 2x. I can simplify this again. E to the x times x squared plus 4x plus 2. And you guys are gonna hate the next part. It's gonna be great.
Of course we are.
Yeah.
Is it not a minus
Where?
in between the two?
No, it's plus for product rule. It's minus when you're doing quotient.
You mean,
Yes. Yeah. 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 Yeah.
Oh, and hold, do like negative b plus minus the quadratic.
Yes.
no, we don't.
Yes, you do. Yes, you do. Yes, you do.
You're way too happy about that.
I've been looking forward to this. You guys trying to factor it and then slowly realizing you can't and you have to use quadratic form.
That's like not in my vocabulary.
It is what it is.
Why can't you just leave it?
What? We're trying to find where it's equal to 0.
Alright.
So you have to solve. You have to find where x is equal
You
to.
could use the perfect.
Nowhere. The answer is nowhere.
X
Yeah, I
equals
agree.
negative.
Answer is nothing. Because
Plus
you
or
can't
minus.
solve
Wow,
X
math
plus
people really like that song.
I don't. I hate Pop the
It's already
Weasel.
the weasel.
Huh?
X equals negative. You use it for everything. Minus 4.
Okay. So the dealio right here, we find points of inflection where the second derivative is equal to 0. So where is e to the x equal to 0?
Never.
Never. So I just had to figure out this guy. Well, it doesn't actually factor. Sucks. So you must use quadratic form.
You could use the other.
X equals negative b plus or minus square root b minus minus 4ac all over 2a. Negative 4 plus or minus 4 squared 16 minus 8 square root 8 all over 2. What?
Got rid of it. Yeah, it doesn't exist.
Exactly. That's why I said you would hate it. Because you must use it.
Just get rid of it.
Let's simplify a little more. Negative 4 plus or minus 2 root 2 over 2, which is just going to be negative 2 plus or minus root 2. I'm sorry, that's really, let me write it under here. Equals negative 2 plus or minus root 2.
You could do the other way.
What? What other way?
If you do the perfect factor rule. Perfect square rule.
No.
Describe.
You get that in one step.
Describe what?
The perfect square rule.
Yeah, okay, so what do you do?
You move the 2 to the other side, so it's negative 2. It's x squared plus 4x plus 4, and then that's that. And you just quit.
Oh, solve by completing the square.
Yeah. Oh, complaints.
So it's like square rule.
It's like I don't the quadratic.
Oh yeah, couldn't you?
It takes like
Solve by, yeah, completing the square, that's fine.
Yeah. Quick math.
Sometimes I like torturing. This is a good torture, because you know it, because it's not even calculus.
But like, let's say you weren't here.
The SAT is good torture because it's fun.
I know.
I'll take the partial credit if I guess.
Okay.
I have to second that.
Okay, so we have our value. I must use a number line. Do not knock, don't put your calculators, don't get your calculators out now. What's bigger? Negative 2 plus root 2 or negative 2 minus root 2?
Definitely
Plus
plus.
the first one.
The one that's bigger, right? The negative 2 plus root 2 is definitely bigger, so it's on the right side. And then negative 2 minus root 2 is definitely smaller, so it's on the left side. Okay, those are where my second derivative equals 0. Don't forget, we're trying to find the points of inflection. So I just have to figure out like a number to plug in so I can figure out multiplicity. Both of these are negative, right? So I can plug in 0. So would that give me a positive or negative number?
Positive. Wait, actually, I don't know.
I'm plugging in right here. If I plug in x equals 0, because these are both negative right here.
Positive.
Let's see, e to the 0 is 1, 0 plus 0 plus 2, oh, it's positive, which means this is negative and this is positive. Because what we're doing is taking a continuous function, e to the x, exponential, multiplying by a polynomial, a quadratic. So no, it's gonna be like a weird graph, but it's gonna be continuous. That's how I know it's gonna be using multiplicity, plus minus, plus minus, plus minus. Because I know there's no vertical asymptotes, there's no like crazy going to infinity things happening. Now that I have that, okay, so I know that a positive second derivative, if you're positive, what do? Smile?
Smile.
Smile, that's probably not the first thing you said. Okay, smile. And if you're negative, you probably frown. I see that every day, and you're happy you smile. Okay. So I see I'm changing concavity. Both of those are going to be points of inflection. All right, the first one, let me take negative 2 minus root 2. That's my x value. To find the y value, you plug it straight into our original function. So that's just going to be e to the negative 2 minus root 2 times negative 2 minus root 2 squared. I'm going to leave it that way. What? Oh my gosh. Okay, so we're finding the y value, and I'm plugging into the original function right here. This is my x I'm plugging in. Yeah.
That is so evil. Actually,
It is what it is. This is not what?
Is the square?
Only this is my x value. Because remember, our original function was e to the x times x squared. So I'm plugging in negative 2 minus root 2 for x. That's what my highlight is showing. And then the second part, well, I have negative 2 plus root 2. So the y value, well, let me just plug this in for x. There. This is my y value. Right? This is my x value. And these are my points of inflection. Right? These are the places where my second derivative is 0, and I'm switching from concave up to concave down. Okay. The next page shouldn't take too long. We're looking at some graphs. We use them to estimate where certain things are happening. Do we have questions over this one? I mean, I don't know. It is what it is. Trying to show you a little bit harder problems so you can understand the ones I assigned. This was a hard problem, yeah. Showing you a hard problem. So then you can understand the easier ones. Because if you understand, find the first derivative, then take the derivative of that to find the second, set it equal to 0, find where we could have points of inflection, okay, plug in, see our concavity. If we're switching, that's where we have a point of inflection. How do you find the actual y value or point? Take your x, plug it back into your original function. That's it. That's the whole method. But you get bogged down in the algebra of it. That's why. This looks hard because I used an exact number, negative 2 minus root 2, instead of using the actual numbers. I don't know. If it makes you feel better, right? If it makes you feel better, we could say negative 2 minus root 2 is like negative 3.141, and negative 2 plus root 2 is negative 0.586. I don't know. If that makes you feel better, sure, by all means, whatever. But I like using the exact. Then at the end, you can decide how precise you want to be. Yeah. Okay, right, so example 4, use the graph of the function f to estimate, so keep in mind we're just going to be estimating, so using our eyes, where f prime and f double prime are 0, positive, and negative. So let's make sure we understand what this means. F prime, this is just your slope, right? The first derivative is the slope. The second derivative tells you concavity. It tells you, are we a bowl facing up? Are we a bowl facing down? It's intense, all right. Okay, so keep in mind, this is the graph of f, right? If in physics, this would be your position time graph. So let's start with A. A is asking for, we're discussing our derivative. So I need to know, where is our derivative? 0, I need to know where are we going to be increasing and where are we going to be decreasing. Okay, so those are the three things it's asking, right? Estimate where it's 0, positive, and negative. So positive means increasing. Negative means decreasing. So let's start with the easiest one. How can I find where my first derivative is 0? Elliot, how can I find this?
Find your first derivative is 0 when the slope is nothing.
When the slope is 0.
0.
Yeah, where's the slope 0?
Slope is 0 when it's right there. Yeah, there and there.
Yeah, so it's where I'm switching, it's where I have a max or a min. And we have to estimate where it's at. So, roughly it seems like it's at -1/2 and maybe positive 1/2. F prime is 0 at these two places. So it seems like this is happening at x equals -1/2 and at x equals 1/2. That seems like where we have 0 slope. Okay, and then we just need to know where is our slope increasing, aka, right? Where is f prime greater than 0? Where do we have a positive slope? -infinity to -1/2. And then 1/2 to infinity. Perfect. So this is the place right here. This is where we are increasing, right? Because it's going up. I should color code. And then I need to know where are we going to be decreasing. Right, so what I'm asking, good, so where is this less than 0? So it's going to be less than 0 when the slope is negative, so it's the middle part where we're going down in between them. So that would just be from -1/2 to 1/2. Okay, half done with this problem. The second half is now talking about concavity. Okay, where is our second derivative 0? Where is it positive? Where is it negative? Let's see. Okay, so B is asking for where is our second derivative 0? Where is our second derivative greater than 0? Where is our second derivative less than 0? So remember, if our second derivative is positive, greater than 0, it's going to be facing up. If our second derivative is negative, which is less than 0, it's going to be facing down. So, can we identify where the concavity is changing? Like, where are we changing from a concave up to a concave down, or down to up? Well, so at that point is where we have a min or max, right? But remember the first thing we did today, where I drew this guy right here, concave up to concave down. Where am I switching concavity?
At the middle point.
Yeah, at the middle point. So you see where we have an upward bowl, where we have a downward bowl. So I need the place in the middle where I'm changing from an upward to a downward bowl. So you can visually see where this is occurring. Right, so here is where I was going, where it's facing down. I'm going to get to in a moment. And then this portion right here that I'm trying to color, I know this is super messy, I'm sorry. This portion right here is where we're facing up. Do you see the upward bowl versus the downward bowl? No, okay, that's fine. Downward bowl versus the part of the upward bowl. Where, at what x value is my concavity changing? At 0, perfect, at 0. So at x equals 0, that's where my concavity is changing. So, I should say equals 0. At x equals 0, this is my point of inflection because this is where I change concavity. Question, yes?
I understand like why that's the point of inflection, but why couldn't you say that it was like a little bit lower, a little bit higher?
Well, we're estimating, right? So if I knew the actual graph function, I could find out algebraically. We're just supposed to be estimating, so it's like about there. It's about right in the middle, you know. If we actually had if we had the equation, we'd do what we just did. But this is more of a conceptual question. Do you understand what it means? to be a point of inflection. Okay, so where do we have positive concavity? Where is our second derivative greater than 0?
From 0.
Yeah, 0 to positive infinity, and then we are down concavity, facing down from negative infinity to 0.
So how would you write it out?
What?
Like the concavity and then
So this part right here that I just erased, that part, this was trying to show you like what does this look like to have you recognize that that's that part. It's also the symbol that we use on the number line. Yeah.
we write that instead of the
You should write f double prime greater than 0 and f double prime less than 0. Okay, last example. Maybe we can do an example problem or two off the review. Okay, so example 5. Using the graph of the function f prime to use it to estimate the intervals on which the function is increasing and decreasing. Also estimate the x coordinates of all local extreme values. Okay, so this is f prime, which means that this should be y prime right here. This is the graph of the derivative. This is the graph of the derivative. So, let's see. The first thing I want to do is, let's see. I want to know where it's increasing, where it's decreasing, and then estimate the coordinates. Okay. So I'm looking here, and since this is the graph of y prime, a couple of things that we know. We know that when the derivative is greater than 0, what is happening with my function? When our derivative, when our slope is positive, is greater than 0, we know our function is going up. Okay. Oh my god, what? When our function is going up. And when our derivative is less than 0, this means our function is going to be going down. Okay. So, for instance, like at x equals 0, right? I know that on the left side of, I don't think that's a good example. No. If I had another graph, right? If I had another graph and like a number, let's say C, and if it was positive here, negative here, that would tell me I'm going up, then down, it would tell me I have a maximum. All right, so looking at the slopes, this is looking at the slope, it's looking at the first derivative. So when I'm switching from being positive to negative, that's where I'll have a maximum in. So, okay, so when our first derivative is greater than 0, I know that's when our function is going up. So let's figure out where our derivative is greater than 0. All right, this is the only place where it's greater than 0. This is where our first derivative is positive. So this is when my function is going up. This portion right here, this is when f prime is greater than 0. Right, so this portion right here, this is when f prime is greater than 0. And then that means the rest of this, all of this is below the x-axis, which means this is a negative slope. Remember, this is the graph of the derivative. It's telling me how our original function is changing. You can't see the original function right now. All we know is like the slopes at all the points. So, since I have a derivative that's less than 0, I know that all of this portion, this is when our derivative, is less than 0, so this is when we're going to be decreasing. So if I want to draw a number line down here, at the bottom, I think that'll help. So at negative 3, I'm switching from a positive derivative to negative. And then at x equals 3, I'm switching from a negative derivative to a positive. So if I'm looking, so this is derivative. So if I want to talk about my actual function, if I'm switching from going up to going down, that means I'm at from going up to going down, I'm at a max. I'm at a max because it's going up, going down, going up. That means I have a maximum here and I have a minimum. So part A is asking, where is our function increasing? Well, where are we increasing? Yeah, exactly. You're increasing, so I'm color coding, you see the red? Our function is increasing when our derivative is positive. So this is the graph of the derivative. This is the graph of the derivative. So whenever this graph is positive, that means our original function is increasing. Whenever this graph is negative, that means our original function is decreasing. So we're increasing when y prime is greater than 0. So as Tal said, this is happening from negative infinity to 3, negative 3, union 3 to infinity. And then we're going to be decreasing whenever our derivative is negative. So just between negative 3 and 3. Oops. Decreasing when y prime is less than 0. So this is going to be from negative 3 to 3. Is this confusing? Are we okay? Maybe? Yeah. It's just weird because it's the graph of the derivative, not the actual function. And then part C is asking to estimate the x-coordinates of all the local extrema values. Did we already do that? Surprise! Our maximum is at x equals negative 3. And our minimum is at x equals 3. Woo-hoo, okay, that's it. So we have 15 more minutes. I think we can get through probably at least 2 of the problems on your review. Yeah. Let's do it. Let's do it. Do we need to like stand up and do the wave? I see you're tired. Yeah, stand up and do the wave. Do it. Do the wave. So we're doing 4.1 to 4.3 review. 4.1 to 4.3 review.
I don't know. I have baseball practice, and then I'm gonna go home and just like watch.
Oh yeah. Do you guys see all this stuff right here on my board? So all of this is uploaded. I have the practice test made for you. It's uploaded. This is 2 things about 4.4, 2 things about 4.6. So don't get alarmed when you look up MyJack and there's 50 things.
It's okay.
We're gonna go through all of it anyway in class, so it's all good. Just warning you.
This isn't 2, right?
No, it's what we're going over together. It's like the practice quiz, more or less. That's what it is. It's a practice quiz. 4.1 to 4.3 review worksheet. I gave this to you the first day of class.
Which are the ones that are due? Is it
They're the
1, 4, 2,
ones.
4, 3, and then
They're the ones in the book.
Oh.
It's the 4 assignments from the book.
Okay.
I've given you 2 review because I wanted to do all of it with you. So try to overplan a little bit. The more practice together, the better. Are you a bird? Just chilling up there? Okay, sure. But are you okay? Yeah. You're like a bird. You're like a canary. Just sitting up at the window.
You said stretch out.
Yeah, okay, I did say that. That was my bad. All right, use analytical methods to find extreme values of f of x. All right, on the interval 0 to 7 and where they occur. Okay, ready? Extreme values. Let's go through the extreme values. So, how do I find absolute mins and max?
You find the first derivative.
Find the first derivative. Exactly, you find the first derivative. 2x minus 6. Then, oh my gosh, let me actually factor this out. Factor this out. 2 times x minus 3. Then we look at, we'll have critical points whenever my first derivative is 0 or undefined. This is a polynomial. It will never be undefined. So I set it equal to 0. Notice the 2 doesn't give me an answer, only the 1 factor with an x does. So I have a critical point at x equals 3. Something interesting is happening here. Is this between my bounds?
Sure.
Yeah, it's between, right? Because our bounds is 0 to 7. 3 is between 0 and 7. So to find my absolute max and absolute min, I'm going to plug in 0, 7, and 3 into my function, whichever is the biggest, max. No. This is from 4.1. I know, it all meshes together. So f of 0 is negative 5. F of 3 is negative 14. And f of 7 is 2. So I see this is the highest, this is the lowest. Alright, so this has to be my min, this has to be my max. So we plug in our critical points and our endpoints, and that's how we find absolute extrema. If we want local, we do the number line, blah, blah, blah. Yeah, and then concavity is double derivative. So that's how you tell. Okay, so absolute max is equal to 2 at x equals 7. Absolute min is negative 14 at x equals 3. I think we could do more. It took like 30 seconds. That's great. Cool. Ready for number 2? Okay, first, what does the mean value theorem say? What's the mean value theorem? MVT.
Find the average. Find the derivative.
Okay, can we reword it? So you're not wrong. I'm just I'm looking for a very want to be precise and include all the parts of the definition. Mean value theorem can be applied. Okay, so if you have a continuous function and you include the end intervals, okay, and you take the average between your two ends, if you take the average between those two, that secant line has to equal at least at one place the tangent line. Okay, let me rephrase what I just said. So, in order to satisfy the mean value theorem, you have to have a continuous function. It can't have any holes, can't have any discontinuities, has to be differentiable. Okay, so we can't have any cusps or corners in our interval that we're looking at. So as long as it's continuous and differentiable, and at the endpoints it's defined, you can take the derivative. It's just like the slope formula, and then you can find the place, right? Which x value is our magical place where its tangent, its derivative, is actually the average derivative. That's all it is. So, A, does this satisfy the hypothesis of the mean value theorem? Okay, so remember, it has to be continuous between our domain, and it has to be differentiable in our domain. We're going from 0 to 1. Trick play, this is a polynomial. It's always differential, always continuous. But if this was like a cusp or whatever, and the cusp occurred between 0 and 1, we wouldn't be able to apply it. But if this was like a cusp, and the cusp occurred way to the left and was not part of our domain, we could still take the mean value theorem if the domain itself is differentiable at that place. Okay, do you see what I'm trying to say? Don't count out an equation just because it's an absolute value and is a corner. If we're not including 0 where it's not differentiable, we'll be okay. This is a polynomial, so it is different. It does satisfy mean value theorem. Okay, so now that we know it satisfies, we have to find the value of c in the interval that makes this true. So that means the derivative at one point is going to actually equal the average slope. Right? So the derivative at a single point has to equal the average for my whole domain. So what I'm going to do, let's see, my derivative, I'm going to take derivative of the original function, is going to be 2x plus 4. How did that happen? 2x plus 4. So if I want f of c, so if I plug in c in place of x, I have 2c plus 4. This is the left side of my equation. And I know this has to equal f of b, so f of b is 1 minus f of 0 over 1 minus 0. This is the right half. Right, my highlight is my left. C is what I'm solving for. C is this special number where its derivative is actually equal to the average. What? The left side? Yeah. I don't want to leave an x value in there because, the book has very, I don't know, this is its nomenclature. It's how it writes it. It wouldn't be bad. You just have to know that this is actually my number. It's not being a variable or extending or anything like that. You still have 5 minutes. Don't worry about it.
It's the same thing as doing these substitutions.
What?
It's kind of like doing these substitutions.
No, I'm just trying to solve for which value. So look at 4.1 in your book. It just uses c. Because it is a number, right? C is a specific single number, where x normally stands for any part of my domain. Okay, so in order to solve f of 1, do we know what f of 1 is?
It's 2.
F of 1 is 2. F of 0, oh, I'm sorry, I tricked you, it's -3. Okay, so 2c plus 4 equals 2 minus a -3 over 1. So I have 2c plus 4 equals, let's see, 2 minus a negative is 5, minus 4 on both sides. So I get c equals 1/2. Cool. That's it. Just write c equals 1/2. Because we're solving for which value satisfies the equation. So exactly halfway on the interval, it satisfies the average. No time to do this one. Yeah, we got 5 minutes. Let's do it. We'll stop after number 2. Okay, we'll do it. We'll do it. For each of the following functions, there is lots of things to find, but fear not. Find the local extrema. Be specific. The intervals where it's increasing. Intervals where it's decreasing. Intervals for which it's concave up. Intervals where it's concave down. All points of inflection. So we're putting this all together. Oh my gosh. Okay. So, local extrema. Think about how we find the local extrema. First derivative. So take the derivative. Found the first derivative. Let me actually fully factor it. No, -2. And I know critical points occur where our first derivative is undefined or 0. This is a polynomial. Polynomials are never undefined. So just have to set it equal to 0 and see what my critical points are. Alright, you set each of these factors equal to 0. So your critical points are 0 and 2. And remember, it's not absolute. We're doing local extrema. So I have to do a number line. So if I plug in, I don't know, what's the easiest thing to do? How about a negative number? Any negative number. So if I put in, okay, sure, we could do 1. Put in 1 into right here. So I have a negative times a negative. So it's going to be actually positive when I plug in 1. So I'm not actually doing the full like math out. I just was plugging into right here, right? Negative 6 times 1 is a negative number. 1 minus 2 is a negative number. So a negative times a negative is positive. So. What? This one? Okay, so we plug in 1. I get a negative and a positive. But you get -6 plus 12 is 6.
Oh, we get positive, sorry.
Yeah, you get positive still. Any number between 0 and 2, if you plug it in, you get positive. It's just easier to like use the factors. Okay, multiplicity plus minus, blah, blah, blah. Okay. Now we have the first derivative drawn out plus minus. We can talk about what's happening with my actual function. So notice I changed colors. I'm not talking about the derivative anymore. I'm talking about the function itself. If I have a negative derivative, that means my function is going down. If I have a positive derivative, that means my function is increasing, right? Positive increasing, you're going positive slope, you're increasing. Negative slope, you are decreasing. So if I'm going from if I'm going down then up, that means that had to be a min. If I'm coming up then down, that means I reached the top of a hill and I have to have a maximum. Ooh, why is this happening here? Oh my gosh. So part A is asking for the local extrema, which we just found, right? We said our min is at 0, so f of 0, plug in 0 into your original function, you get -3. We said our max is occurring at x equals 2. So if I plug in the value into my function way up here, right? We're plugging into our original function. Plug in 2, we should get 5. 2 times 4, 24. -8 minus 3 is 5, yeah. 5. So I'm just going to write out this first answer, and then we'll definitely start back here tomorrow. So max is at f of 2 equals 5. Min is at f of 0 equals negative 3. Cool. So make sure you bring this as well as the 4.1, 4.2 review. We'll get through all of it tomorrow, and then if we have time at the end of class, we will go over questions from homework. Cool. See you guys later.